Welcome to the SI2 OpenAccess Workshop Series. In this episode, we'll demo how to add real-time constraint monitoring to an OA user script with only minor changes to the script's core. The OA API is much more than a database. It's an entire EDA tool ecosystem, but today we'll be narrowing our discussion to some often overlooked classes in the OA API. Constraints, and observers. For this demo, we'll be using a hypothetical OA-based user script, HOUS, that we'll call HOUS for short. We will be adding background rule monitoring to HOUS. The core of HOUS is an OA script function, demo HOUS. This OA script function, it will use a tech.DB and an OA design database. For simplicity, all that this core function, demo HOUS, does is call OA 4 times and create 4 shapes and then finishes. So there is no complexity at all in our core function. As the basis for today's demo, we'll ask the question, how can we enhance our script to know if design rules are violated when it generates shapes using the core function demo HOUS? Now, the old school ways to determine rule checking are, number one, you could go out and buy a DRC checker using an OA to GDS and then writing rule deck and having the whole thing get processed could be quite expensive. A second way would be to write our own rule checking code and embed it into our demo HOUS core script. That would mean we'd have to insert logic into demo HOUS to handle checking and read DRC rule decks. And if we add new constraints into it, it'll get more and more complicated. Not only is that expensive, but our simple core algorithm starts turning into a bowl of spaghetti. But OA has a better solution. OA provides a built-in way to implement background rule monitoring using oaObserver-based constraint checking without having to turn your core layout generator algorithm into spaghetti. Before we look at our demo solution, however, let's get a little more familiar with OA constraints and observers themselves. We'll be using a very simple single layer constraint, the min spacing constraint depicted here. It involves 2 shapes on metal 1, A and B, separated by distance S. The constraint definition that we'll be using is if S is less than or equal to 500 dBU, a min spacing violation exists. To create and configure the min spacing layer constraint, we need 4 settings: the layer number, the OA layer constraint def, which is a predefined name, the hard flag, which tells us that this constraint is required or not required, and the constraint value, which is the 500 integer distance. Also, in our case, we'll add our rule to a tech.DB in its FoundryRules constraint group. OA has an extensive list of predefined built-in constraints, about 150 or more of antenna rules, area rules, clearance rules, etc., all of them already predefined in OA. It should also be noted that constraint defs are not limited to layout, because user-defined constraint defs are possible. You can create a constraint for almost anything. The number of pins on an OA net, the RC time constant on an OA term, the number of flops in a scan chain, the bus naming convention, almost anything you want to constrain. But for this demo, we'll just be using the OA min spacing constraint def. So let's prepare a hard minimum spacing of 500 dBU for all shapes in the Metal 1 drawing layer on this tech.DB. Since we are applying this constraint for our entire OA technology, we use the OA tech tech.FoundryRules constraint group, and we place our constraint inside of that group. Note that OA constraint groups can contain many OA constraints and can be associated with many OA classes, such as designs, nets, shapes, wafers, even other OA constraint groups, not just OA tech foundry rules. Thus, OA constraints overall can represent very complicated electrical, process, timing, reliability, testability rules, not just the simple min spacing rule in this demo. We now know how the min spacing is defined and created, but the OA constraint system really shines when we combine it with an OA observer. That's because OA observers are triggered by changes to the OA database, so they seem to work in the background when something in the OA database is changed. Think of it like an outside OA monitor that when a shape is created, OA notifies our observer and it can check the shape against constraints, and the observer can flag if there's a problem. Also, OA has many more than just shape observers. There's observers for dozens of OA objects such as nets, libraries, text, designs, pins, terms, ints, figures, which makes the background monitoring of most OA objects easy to implement. So now let's put all the pieces together and walk through how our OA observer-based constraint monitoring solution works. We'll begin with our demo HOUS algorithm and the base OA stuff as before, but instead of spaghetti code, we'll create a constraint in the Foundry Rules group. And we're going to save it in the TechDB. Next, we instantiate myShapeObserver. It's tied to an OA shape class, and so our observer will be notified on post create. That is, after a shape is created, our observer will get called. So for this demo, as soon as our observer object is initialized, it will create a demo display to help us see what's going on inside the observer object. Now let's step through how this application works. After setup of the OA TechDB and library and the design, we get our core and we call it. The demo house OA script then calls OA 4 times. And then OA creates 4 shapes. After each shape is created, OA notifies our onPostCreate method in myShapeObserver. It does that 4 times. And then the shape observer goes through its function, the onPostCreate, and it checks the constraints for each shape it gets. So it's going to check the constraints 4 times. After checking, the observer displays the shape and reports any violations. So it updates the display every time. And then on the 4th one, the observer is going to find a violation because that shape is too close to the other one. So it's going to record the violation for us. Notice that our solution here has left our core demo house algorithm untouched, but we got rule monitoring without spaghetti in our core. Now let's switch over to the live demo. It begins here in main. It does the creation of the library and design. Next, it's going to create the simple min spacing constraint. And we'll see that there's a breakpoint inside of that. We'll stop at that. We'll see we get all the numbers that we need for our creating our constraint. Here's the definition we need for the constraint from OA min spacing. We're going to get the spacing rule itself, the constraint. We're going to get the constraint group from our foundry rules in the technology. And then we're going to put the constraint in the constraint group. And then we'll have finished with doing that part. As we saw before, that was by adding this. So at this point, we're at this point in the code. Next thing that we do is we're going to start up the shape observer. So we will see here the shape observer. Here we start up the shape observer. But we'll notice that the first thing that the shape observer did in the init was create the demo display window right here, right over here. All right, so we are going to be now inside of our demo house. So we're going to start over here. We've done this part, we've done this part, we've done this part. Now we're going to start over here for this. We're going to run through this 4 times. At this point, we're about to call the rectangle shape creator. That's an OA function. It will trigger our observer. Notice that it went to the onPost create and it drew our shape in our display right here, drew the shape. And now it's going to call the constraint checker for that shape. OnPost create, it's going to check the constraint again. This time, when it checks the constraint, it's going to find that there's a distance of 4,000. If you look over here, there's a distance of 4,000 between the 2 shapes. That's going to be okay. And now we're on the 4th shape. So the 4th shape is going to have a problem because it's too close to this shape over here. And then we run again. It says, uh-oh, this is only 200 from the other one. That's going to be a problem. So upon returning, it's not okay, and we're going to record this as a failed shape. And we're going to draw the failures on the display. So we'll see that the failure gets flagged on our display, and then we return back to our main function. And that was the last thing we did in our main function. So we are going to exit out of this thing. So now we exited out of our main function. It created the 4 shapes, and our observer detected that there's a problem here, and it showed the problem. And then now we're going to ask the observer to tell us what happened during the running of demo house. The reports, it writes the reports, and over here it shows it saw 4 shapes created, and then it saw 1 constraint violation. So we've seen that by combining oaObserver, constraint, and tech objects to run smart monitors in the background of our user application, our core function can focus on layout while at the same time our shape observer checks for compliance with our Foundry technology. Yet we added lots of functionality but hardly touched our core. So to quickly summarize, OA constraints can be defined and saved in an OA database. With observers, constraints could be monitored in the background with only minor changes to a user's script's core algorithms. Observed violations can be dealt with in real time or afterward, and user scripts or AI agents can self-check to ensure that they generated designs that meet specified constraints. Agentic AI can use constraints to mitigate hallucination or drift. If you have questions or wish to investigate more, consult the OA reference implementation documentation available to SI2 OpenAccess Coalition members.